All right, ladies and gentlemen, recording has started. Here we go. So, like I said to you guys earlier, in grading your quizzes, I feel we need to spend a little bit more time talking about some of these concepts dealing with acceleration and how it relates to a motion, a real world motion out there. Look at some numbers. How do we get this? How do we get that? So I wanted to take a couple minutes and do that today. We're going to start with this picture of this guy riding his bike. And it says, what is the acceleration of this biker as he rides along the path? So we talked last Friday, we introduced the concept of acceleration. And what did we say that acceleration tells us? What is acceleration? Okay, so acceleration is the rate of change of an object's velocity. So a rate of change of an object's velocity. Right? So Sam, what did you say?
The thing being like weird.
Oh, it blinks?
Yeah.
It blinks when I'm recording. So it basically just takes like a bunch of screenshots real fast, so the cursor blinks while I'm recording. So yeah, it takes like, you can change the rate, but I think it takes like 8 pictures a second or something like that. So that's what it's doing. Alright, so acceleration is the rate of change of an object's velocity. But more importantly, we talked about that we can summarize that definition with this equation, right? Delta V over delta T. The change of an object's velocity, that's this part, right? That's the delta V part. And then we kind of talked about the idea that the rate is this part here, right? That rate is a time factor and stuff like that, okay? So, in looking at this guy riding his bike, based on the information that it is given to you in the picture, you should be able to tell me what the acceleration of this bicycle rider is. So talk to the person next to you for 30 seconds and see if you guys can determine what is the acceleration of this biker. Go. Alright, so we said that acceleration also is going to tell us how much velocity changes each second. So looking at this data, right, it gives us that at time equals 0, that biker is at rest. And then 1 second later, he's now traveling 2 meters per second. A second after that, he's now traveling 4 meters per second. And a second after that, he's now traveling 6 meters per second. So, how much is velocity changing each second? 2 meters per second. So that means that his acceleration is 2 meters per second squared. Remember that we said that writing 2 meters per second squared is the same as if we were to write 2 meters per second for every 1 second that goes by, because acceleration tells us how much velocity changes each second. Okay. Good there? Now, remember, these numbers up at the top are only telling us how fast something is going, but not about how far it's going. If we look at this picture, right, during the first second, how far does he go?
1 meter.
Only 1 meter. But the next second that goes by, now he's at 4 meters from his starting point, right? So he went an additional 3 meters, right? And then in the next second that goes by, how much further did he go that time? 5 meters, right? So we see that even though his acceleration is constant, that the velocity keeps changing by the same amount, the distance that he goes keeps increasing because we keep going faster and faster and faster. Okay? Good there? And that's when we got into like kinematic equations and delta x. How much is delta x when acceleration is this much for this time? Blah, blah, blah. Okay? All right. Next, let's take a look at this guy right here riding his bike. It's the same guy, just different situation. Okay? So, based on this information here, information about what he's actually doing in each situation, okay, and I gave you some actual numbers up here, you should be able to calculate for me what his acceleration is in part A when his speed is increasing, and in part B when his speed is decreasing. So we just said that acceleration tells us the rate of change of velocity, right? That's supposed to be V. Okay. But we said that we can also expand that out to make it look like this, right? Because that's how we calculate delta V, right? V final minus V initial. So, based on this information I've given to you here for this guy riding his bike, talk to the person next to you and calculate what is his acceleration in each situation. Talk, go.
Situation. So, its acceleration is 20? 220?
No, what? Yeah, so 6 minus 4 divided by 2.
Maybe it's the
So
same.
2 divided by 2.
Are those going to be 2 minus 4? Maybe 1 is negative 1.
All right. Are we okay with where I got these numbers from? In the first example, it tells us that speed is increasing. All right. This is kind of like a sort of OCD sort of thing, but I'm going to change something right there. This is going to go away. This is going to come over here. And this is going to come over here. Okay, just now they're like red and blue together. All right, so. Because I know that somebody's out there going, wait a minute, this one's highlighted in pink, but I circled this one with red. I know somebody's out there doing that, all right? So I'm going to try and alleviate this. No, it's somebody's out there, right? My visual learners are going, wait a minute, what's going on here? So, all right. It tells us, in this case, that speed is increasing, right? So that would make this V initial and this V final, right? Because he's going faster. And then in the second example, right, when speed is decreasing, if this is how fast he's going originally, that's how fast he ends up going. Good there, right? So when we plug this in, for those numbers in for the acceleration, right, what do we get here when we calculate the acceleration here?
1 and
So that's going to be positive 1 meter per second squared. But then when we plug in things to this equation over here, right, 2 minus 4 gives us what on the top? Negative 2, right? Divide that by 2, and so we end up with a negative 1 meters per second squared. Okay? Good there? Acceleration positive here, right, because he's speeding up. Acceleration negative here because he's slowing down. Good so far? Okay. Now I'm going to change something up on you. Okay. Here's a lady riding her bike. So the first question says, how is the velocity of this rider different than the previous example? So what's the one obvious difference between example 1 and example 2? Which way is this girl riding her bike? Opposite way, right? So, in this case, right, opposite direction of the rider means that what are we going to say about her velocities? They're going to be negative velocities. Because remember, the negative sign on velocity, or the positive sign, is only telling us which direction. Okay? With that being the case, right, again, two examples. Oops, sorry. Sorry, visual learners. First example, speed decreasing. Second example, speed increasing. Okay? Based on that, now talk to the person next to you and figure out what are the accelerations in each of these cases. Go.
First one's -1. Second one is 1.
First one's
-1. Second one's 1.
I like -3.
Second one's 3.
If you have -1. So -4.
Oh,
that's where it's the velocity.
Why did he choose the field?
So if you have, yeah, choose plus okay.
No, to change the thing. Yeah. What the same thing.
Wait, so why? That's fine.
Okay, well, let's talk about that.
Oh, because it's closer.
Right. So, in the first example, in part A, right, it tells us that speed is decreasing. So if we go back up here, right, we said the one obvious difference about this example and the previous example, because we're going in the opposite direction, that means that velocities are negative, right? So if this guy starts off at a -4, right, and his speed is decreasing, that means, Jamie, those values have to be getting closer to what? 0. -2 is slower than -4. It's just slower which way? In the negative direction, whatever we call the negative direction. Even though, when we look at it on a graph, it would appear higher up on the graph. Remember, the positive and negative tells us nothing about how fast. It only tells us which way. So, -2 is the final velocity here, which is slower than -4. So if I take those numbers and plug them into the equation for acceleration, right? We said that acceleration, v final minus v initial over t, right? -2 is the final velocity, -4 is the initial velocity. So on the top of this fraction, -2 minus a -4, you can't change this minus sign. That's part of the formula. You can only plug values into that formula. So if you subtract a negative number, what are you really doing mathematically? You're adding, right? So on the top of this fraction now, you end up with +2 over 2, and that means that the acceleration for this first part is on the second part, though, -6 is faster than -4. It's just faster in the other direction. Even though on a graph, -6 would be lower than -4. That means that speed is increasing if we go from -4 to -6. When you take that and plug it into the formula, oh, sorry, did this backwards. This would be the final velocity -6 minus the initial velocity, which was -4, right? Minus 6 minus a negative 4 means we add, right? So on the top here, we end up with negative 2. Over 2 on the bottom for the time. So we get an acceleration of negative 1 meter per second squared. Good there? Okay? But remember, speed was increasing in part B. But we ended up with a negative acceleration because you can't tell just from the acceleration what is happening to the motion. It's a combination of both. Sorry, new program. Going on here. There we go. It's a combination of both the velocity and the acceleration. Things are going to speed up if they have a positive acceleration and they're already moving in the positive direction. As long as both of them have the same sign, that means speeding up. It could mean speeding up in the positive direction, but it also could be speeding up in the negative direction. So negative acceleration could mean going faster, just depends on which way we're originally going. So as long as velocity and acceleration, when we measure them, have the same sign, we end up speeding up. But if they're opposite signs, both cases result in slowing down. Good there? Okay with that? All right. Next. Going back to this guy on his bike. I want you to talk to the person next to you and draw me a sketch, just a sketch, of what would the velocity versus time graph for these two instances look like. Draw me a velocity versus time graph for these two situations. Just a sketch, doesn't have to be real detailed. You can make it detailed if that helps you draw the sketch, but draw me a sketch. What would the velocity versus time graph for these two motions look like? Velocity versus time graph for these two motions. All right, so we ready? Okay. So, tell me about that graph on the bottom. Why does it look the way that it does? What's one thing you can tell me about that graph from the top motions to make it look the way that it does? This discussion is important. What's one thing you can tell me from the picture on the top that translates into the graph on the bottom? That's good.
They both start at 4.
Okay, they both start at 4, right? So that means, actually, they're not at rest when this graph starts, right? They're already moving, and they both were moving at the same speed and the same direction, so that's why they both start here, right? What else? What's next? What else can you tell me about this graph based on those pictures? Orgo, go ahead.
Same time, and then A is speeding up, so it's going away from 0.
Good. A is speeding up, right? So its graph is moving farther and farther away from 0. Because on this graph, when we cross this line, what does that mean we're doing? Because this is a velocity graph. When we get to 0, that means the object is doing what? It's at rest, right? It's not doing anything. So, by this graph going away from 0, that means it's doing what? Speeding up, right? But on the other hand, what are we seeing about this graph here? Because it's getting closer and closer and closer to what? 0. Okay? Good there? All right. Next. Same thing, but now do it for this lady. What is the velocity versus time graph for this lady and her two motions look like? Ready? Or we need some more time to contemplate. Is the anticipation too much for you to handle? All right, here we go. All right, same process, right? How do we get from those two pictures on the top to this graph on the bottom? What's one piece of information on the pictures in the top that shows up in the graph on the bottom? Okay, Joe, go ahead.
They both start at -4.
Both start at -4, which means, Joe, where are they starting on this graph?
In the same spot.
Same spot, but where compared to the previous graph?
Oh, below 0.
Below 0, right? Because now we're on the negative side of that line because we're going in which direction, Joe?
Well, are they both going different directions?
They're going different directions, or this lady is going the opposite direction from the guy in the previous picture.
Yeah.
Okay? All right. So that's one thing. We both start here, but this time underneath the x-axis as opposed to the previous one. What else?
One's slowing down.
What's slowing down? Which one's slowing down, Jamie? A. And that means that his line or her line is getting closer and closer to what?
0.
Even though it's sloping which way?
Oh,
Even though it's sloping up, right? That still means slowing down on this graph because it's getting closer to what?
0.
0. And if velocity gets closer to 0, that means it's slowing down. And then B, physically, what's B doing? Speeding up. So graph is getting away, right? So if we compare these two graphs, not that one. Sorry, visual learners. Speed increasing here looks like that on this graph. But speed increasing here looks like that on this graph, right? While they slope opposite ways, they are both moving how on the graph? Away from 0. Speed decreasing here looks like that, where speed decreasing here looks like that. Good there? Okay. So anytime speed is decreasing on a velocity graph, we're getting closer to 0. Anytime speed is increasing, we get farther away from 0. Good so far? Okay. Next. Here's a graph. Discuss with the person next to you. What is the velocity? What can you tell me about the velocity during each of those sections? Talk. Go.
velocity for A is speeding up, velocity B is speeding up. But less, it'd be less. Yeah, it's less than C slowing down.
C velocity is fast.
Doesn't matter, it's slowing down. The slope is fast.
It says describe velocity.
It's going down. The slope. Yeah, just 3.
It's actually not 3, it's what?
It's 1/3, isn't it? It's to the right, 1, or negative.
It's -3. That's important. All right, so velocity. What can you tell me about part A? What's happening in part A? Speeding up. What's happening in part B? Still speeding up, but at a lesser rate than it was at the beginning, right? What's happening in part C? Slowing down. Did it turn around? No, because all of these velocities are on which side of 0? They're all on the positive side of 0. So it's always moving in the same direction. Sometimes speeding up, just not quite as much. Sometimes slowing down.
Will you ever know in a velocity versus time graph if it changes direction?
Good question, Sam. Would you ever know on a velocity versus time graph if it changes direction? The answer is yes. Wargo, what does it have to do to show you changing direction?
It goes from positive to negative.
Has to go from one side of the x-axis to the other side of the x-axis, right? If line C continued, right here, if line C continued like this, right, and that was, the x-axis extended, at this point right here, what did that object do? It does change direction because it goes from being on the positive side to being on the negative side. But what does it have to do, at least for an instant? It has to rest, stop, just for, a brief moment, okay? Because in one dimension, you can't go from going one direction to another direction without first stopping. Can't happen, at least in one direction, or one dimension, okay? Good there? Okay, we've already sort of alluded to this a little bit, okay? Acceleration. If you look at this graph, can we figure out the acceleration? Yeah, okay? We already kind of talked about the acceleration during A and the acceleration during B. In both cases, it's speeding up, but how much is it speeding up during B versus A? Which one speeds up more? A, right? On a velocity graph, slope on a velocity graph tells us acceleration. So what do you see about the slope during part A? Pretty steep, right? So it's a pretty big acceleration. It goes up a lot on the velocity side in not a lot of time. But during part B, right, what do you see about the slope? Is it as steep as A? Not as steep as A, right? Is it still speeding up? Yeah, just not as much. But then once we get to part C, right, what happens to the slope during that section? Now, it's very steep, but which way does it slope now? Negatively, right? Making that connection to what we just talked about on that chart that I showed you, here during part A, what can you tell me about all the velocity values? What sign do all the velocity values have here? They're all on the positive side, right? Which way is the line sloping? Up or down? Up, meaning that the acceleration is also positive. And if we have positive velocity and positive acceleration, what did we say that meant?
Speeding up.
That means that that object is speeding up. During part B, velocities are still positive because we're still on the positive side of x. What about the slope in that case? It's still positive, right? Is it as much positive as it was during A? No. But if we still have velocity positive and acceleration positive, still speeding up. But now, in part C, we said that the velocities are always positive, right? Because it's still above the x-axis. But now, what about the acceleration? It's sloping downward. Physically, what does that mean happens? This is slowing down. Good there. Okay? These are concepts that when we went to apply them on the graph or on the quiz, we were a little fuzzy on. Okay? So like I said, I just recorded this discussion, right? So it'll be there posted for you. I also will post my notes like I just wrote here. I'll post those online as well. So if you had, trouble keeping up with the writing and things like that, they'll be there for you. Okay? Good there? All right. Let's stop this.